Hello everyone, today we're going to be going over the January 2025 Chemistry Regents exam. In this video, we're going to be focusing on part B2, which are 15 short response questions. A link to this test can be found in the description of this video, alongside more review videos going over part A, B1, and C of this exam. So if you want to follow along at home, or if you want a full review of this test, please check out the links in the description. That being said, we're going to go ahead and start off with number 51. It asks us, state in terms of electrons and energy state how the light emitted by an excited boron atom is produced, okay? So first of all, what is an energy state? What are electrons? Well, we know that electrons are going to orbit the nucleus of an atom. So in this case, if this is my boron nucleus, it's made up of protons and neutrons, it's positively charged. It's going to be orbited by these electrons, okay? And turns out these electrons are going to exist in certain states, which we call shells, right? So this boron is going to have multiple shells of electrons. So you'll have the first shell of electrons. This is where the first orbital is going to be, followed by the second shell, followed by a third shell, all right? And essentially these are areas in which electrons can comfortably exist in, okay? So this boron has a certain number of electrons, right? And they can exist anywhere within these shells. So what can happen is if an electron gains enough energy, it can actually move up in its shell, right? And the further out you go, the higher energy you have. The further in you go, right, closer to the boron, the less energy you have, okay? So how can a electron magically gain energy? Well, it can be excited, right? It could be excited by light. If light hits this electron, the light energy is absorbed by the electron, and that gives it enough energy and enough excitement to move up in an energy level. And then again, if light hits it, it will move up into yet another energy level, all right? Now here's the thing, right? The opposite can also happen. Let's say that if an electron loses its energy or does not have enough energy to exist in this state, it will then go down and move closer to the center where there's lower energy states. So if I have an electron here and it moves down into the next energy level, right? It moves down into this orbital right here. It's now lost its energy and it's released that energy in the form of light. So state in terms of electrons and energy state how light is emitted. Well, light is emitted as electrons move down in energy level, okay? So if we go in our answer booklet, this is where you're gonna write your answers to this question, we can say how excited electrons emit light as they return to lower energy levels / states, right? So that's all you need to know here, all right? You could also say that the boron electrons lose energy as they return to lower energy states. You could also say that excited electrons move to lower energy states. You could have said that electrons in excited boron atoms release energy as the electron moves from higher energy states to lower energy states, okay? So again, as long as you're moving inwards, you're losing energy. And again, how do you lose energy? Well, you emit it as light. So number 51 and 52 asks us to do the following. It says that the atomic mass and natural abundance for two naturally occurring isotopes of copper are shown in the table below. Number 52 asks us to show a numerical setup for calculating the atomic mass of the element copper, okay? So what happens here is that we're showing a numerical setup. We're not actually calculating it. We don't want to calculate anything, right? That's not what we're being asked to do. All we need to do is just show up the setup or show how you would arrange the numbers to then solve for this atomic mass, okay? So how do you find the atomic mass? Well, you multiply the mass of the isotope, so the mass of isotope, by the abundance. And then you sum it all up together. So we see here how Cu-63 is an isotope of copper, right? It has a mass of 62.93. So I'm going to take the mass of the isotope and I'm going to do 62.93 and I'm going to multiply it by the abundance, which is 69.15%, okay? Obviously, if you want to multiply a percent by a regular number, you need to convert the percent into a number by dividing by 100. So 69.15 divided by 100 is equal to 0.6915. So I'll multiply this by 0.6915, and then I'll add that to my second isotope, which is Cu-65, which again has a mass of 64.93 and an abundance of 30.85%. So I'll multiply that by 0.3085 because I'm dividing it by 100 to get the percent from there. All right. All I have to do here again is just copy and paste whatever I wrote here into my answer booklet. Okay, so here's my numerical setup. I'm going to do 62.93 U, showing that that's the mass unit here, times 0.6915 plus 64.93 U, that's showing the unit for the mass, times 0.3085, okay? It's 3085. This is more than enough work to show how to get full credit here, right? You showed how you calculated it, you would get full points here, all right? Now, number 53 says a technician determined the percent of the natural abundance of Cu65 in a sample to be 31.47%. Determine the percent error of this natural abundance of Cu65 compared to the accepted value shown in the table. So note here how numerical setups, you don't actually have to answer the question, you just have to show the work as if you were answering the question. Now, whenever they ask you to determine something without showing your work, you don't have to show your work. So in your answer booklet, you're just putting in the answer here. So they're asking for percent error. If you don't know the formula for percent error, it's included in your reference table right here. You know that percent error is equal to measured value minus accepted value over the accepted value times 100. So the measured value is going to be 31.47. That's what he measured. Now the accepted value of Cu65 is going to be 30.85. And now you're going to divide that by, what are you going to divide it by? You're going to divide it by the accepted value, which is again 30.85, and then you're going to multiply it by 100. Now, almost made a mistake here. Remember, whenever you're dealing with percents, you need to convert them into regular numbers. So this is actually 0.3147, and this is actually 0.3085, and this is again 0.3085. So all we have to do is just plug that into our calculator. So I'll do 0.3147, remember, as a number, not a percent, minus 0.3085 divided by 0.3085. That gives me 0.02009. Now remember, I want to go ahead and I want to convert this into a percent, so I multiply this by 100 to convert it into a percent. And my answer is going to be 2.0%. Okay, so remember, include the 0.0, you get 2.0%. That's the correct answer here. All right, moving on to number 54. It says that the element beryllium, magnesium, calcium, strontium, and barium are located in group 2 on the periodic table. These group 2 elements have both similarities and differences in their physical and chemical properties. Based on the location of group 2 elements on the periodic table, state the element classification for these elements. So what are group 2 considered? So remember, groups go up and down on the periodic table of elements, and periods go left and right. So this is period, and this is a group. Right, so here we see the group number, this is group 2. Now you should know that group 2 are going to be alkaline earth metals, right? Alkaline earth metals are right here. How do I spell that? Alkaline earth metals. That's what this group is called, right? You know that this group is called the halogens, this group is the noble gases, these groups are the transition metals. So beryllium, magnesium, calcium, strontium, barium, and Ra, I don't know the name for that, but again, all of these are going to be alkaline earth metals. So that's the correct answer here. Go into number 54 and just say alkaline earth metals. That's the name of that group. They're asking you for the name of that group. Right? That's the classification of these elements. They're classified as alkaline earth metals. Number 55 asks, explain in terms of electron shells why the atomic radius of calcium in the ground state is greater than the atomic radius of magnesium in the ground state, right? So let's look at where calcium is. Let's look at where magnesium is. Okay, so calcium is down here, magnesium is here, and it's saying that calcium has a larger atomic radius. Well, what is the atomic radius? Well, it's the distance from the center of the atom to the outermost shell. So we see here how magnesium, this number right here is the electron configuration. So 282 tells me that the first shell has 2 electrons, the second shell has 8 electrons, and the last shell, which is the valence shell, has 2 electrons, okay? What that tells you is that in total there's 3 shells here. So magnesium has 3 shells. This is the first shell, this is the second shell, and over here is the third shell, okay? Now let's compare that to a calcium, right? Calcium, put that in yellow over here, has how many shells? Well, that's 2, 8, 8, 2. That's 4 shells in total. So here we have 1 shell, 2 shell, 3 shells, and 4 shells. If we look at this, the radius between the center and the outermost shell is definitely bigger than this radius between the center and the outermost shell. Why? Well, it has 1 extra shell. So we can just say here that calcium has 1 more electron shell than a magnesium ion or a magnesium atom, and we can get full credit. So calcium has 1 extra electron, get more space, electron shell than magnesium does. Okay, you could have also said that the calcium atoms have 4 shells of electrons while the magnesium atoms only have 3 shells of electrons. You could have said that calcium atoms have more electron shells. You could have said that a calcium atom has 1 more electron shell than a magnesium atom, right? That's all. So remember that the electron shells, the more electron shells you have, the greater your atomic radius is. So in this case, calcium, like I just said, calcium had one extra shell, which is why it was bigger. All right, number 56 asks, state the general trend in first ionization energy for group 2 elements, beryllium through barium, as these elements are considered in increasing order of atomic number, okay? So starting from barium and going to beryllium, right? Did I read that properly? Starting from beryllium and going through barium, okay? So beryllium is Be, barium is Ba, and we have to look at the first ionization energy for 4, 12, 20, 38, and 56, okay? So in this case, we can find the first ionization energy right here in table S. So we'll look at beryllium, which is 900, then the next group in increasing atomic number, remember that this number right here is the atomic number, the next one in increasing order is going to be magnesium. So then we go to magnesium. Over here, magnesium has an ionization of 738. Then we have calcium. Calcium has an ionization of 590. All right, then we go to strontium and barium. Strontium, Sr, has a ionization of 549, and then barium over here has an ionization of 503. So we can see here how beryllium had an ionization of 900, but all the way at the end of the group, we have an ionization energy of 503. So clearly the ionization energy decreases as you move down the periodic table of elements, or down the group, which is through or done by increasing the atomic number. So all you have to do here is just state that trend. You can say that as the atomic number increases, the first ionization energy decreases. And that's all you need to do to score full points here. You don't need to explain why, you just need to state the trend that you see, okay? And if you look at table S, you'll never get it wrong. This one says diagram 1 represents a sample of N2 and the conditions of pressure, volume, and temperature of the gas in a sealed, rigid cylinder with a movable piston. Diagram 2 represents a sample of O2, or oxygen gas, and the conditions of pressure, volume, and temperature in the gas in a sealed, rigid cylinder with a movable piston. So here we have the same setup here. Diagram 1 is just with nitrogen gas. This diagram 2 is just with oxygen gas, okay? Now, number 57 asks us to compare the average kinetic energies of the gas molecules in diagram 1 to the average kinetic energy of the gas molecules in diagram 2. So we know that average kinetic energy is temperature. Temperature just gives you the average kinetic energy of all the particles in the sample. So if we look here, the temperature is 300 Kelvin. The temperature here is 300 Kelvin. So what can I say about the average kinetic energy if that's the same thing as temperature? Well, they have the same temperature, so they have the same kinetic energy. So you can say here that the two samples have the same average kinetic energy. All right, then you can move on with your day. So the KE of this is the same. You could say that it would be equal, anything like that, anything along those lines. Number 58 asks us to determine the volume of O2 in diagram 2 when the conditions are changed to standard temperature and pressure, okay? So right now we're not at STP. Why? Well, because STP is 298 Kelvin at 101.3 kilopascals, I think it's kPa. If you're unsure, like I am right now, you can move up to the front of your reference table and it will tell you that at standard temperature and pressure is 101.3 kilopascals, or in atmospheres, and then the standard temperature is 273 degrees Kelvin, okay? So sorry guys, I was mistaken. It's not 298 Kelvin, it's 273 Kelvin. Regardless, these are conditions that are different from the conditions here. All right, and again, we're looking at the diagram 2, which is for oxygen. So what happens when I change the pressure, the volume, and the temperature to these conditions right here? Well, how do I find that? Well, I can look at my reference table all the way back down. I can scroll all the way back down. And what I can see here is that P1 V1 over T1 is equal to P2 V2 over T2. Okay, so let's write down that formula for us right here, because we're going to work with it. P1 V1 over T1 is equal to P2 V2 over T2. Okay, so why does this matter? Well, this matters because P1 V1 and T1 are my initial temperature, my initial pressure, and my initial volume, and P2 V2 and T2 are my changed volume and my changed pressure. Okay, so this is my initial values. That's always going to go with anything with a subscript of 1. So my initial pressure was 600 kilopascals. So 60 kilopascals. I'll put 60 here. My initial volume was 1.8 liters. So I'll do 60 times 1.8 liters. Okay. And divided by my temperature, which is going to be 300 Kelvin. 300 K. Now, I'm going to move on into P2, V2, and T2. My second pressure is going to be, well, my standard temperature and pressure, which is 101.3 kilopascals. And I'm going to multiply that by my volume. Now remember, I'm determining the volume in O2 after I change these conditions. So I'm finding the volume after it's changed, or I'm finding V2, and this is all being divided by T2, which is again 273 Kelvin. Okay, so this is 273 Kelvin. So all I need to do here is just cross multiply. I need to multiply the bottom by the top here, so I'll do 273 times 60 times 1.8, and I'll set that equal to 300 times 101.3 times V2. So in other words, 60 times 1.8 times 273 is equal to 300 times 101.3 times V2. And then I'll just divide both sides by 300 times 101.3. 300 times 101.3. If you divide and do all this math, which I'm not going to do on screen right now because it's going to take too much time, you'll get 0.97 liters. So that will be the new volume, 0.97 liters. All right, number 59 asks us, determine the pressure in atmospheres of the nitrogen gas in diagram 1. So right now I know that my pressure here is 60 kilopascals, or 60 kPa. If I look at my reference table all the way up here, I can see that 101.3 kilopascals is equal to 1 atm. So what I can do here is I don't actually need to memorize this conversion. All I need to do is just multiply this by 101.3 kilopascals over 1 atmosphere, or 1 atm. All right, set up a dimensional analysis. If I have kilopascals in the numerator, how do I cancel it out? Well, I multiply it by something in the denominator. Right? If I have kPa on the numerator right here, kPa in the bottom right here, they'll cancel each other out. So the conversion factor is to divide your kilopascals by 101.3 to get however many atmospheres that's equal to, right? So if you plug this into your calculator, you're going to get 0.592 atmospheres, so 0.592 atm, or atmospheres, okay? So number 60 to 62, it says the boiling point for a sample of a molecular compound is 80 degrees Celsius at standard pressure. The heat of fusion, or HF, of this compound is 127 joules per gram, okay? So that's the heat of fusion. Compare the potential energy of the molecules in a sample before vaporization to the potential energy of the molecules after vaporization. So for you to vaporize something, right, you're turning it into a gas. Right now it's a liquid, okay? Or even if it was a solid, right? In order for you to vaporize something, for you to literally boil something, you need to apply energy. So because you're applying energy, the potential energy of the system is increasing, right? Think about if I want to melt water, right? If I want to boil water, sorry. I have H2O, which is a liquid, and I'm applying heat, or I'm applying energy, and I'm turning it into H2O gas, right? That means that what I'm left with has a higher potential energy because I implemented or inputted more energy into that system, okay? So the correct answer for number 60 has to be that the potential energy is greater after vaporization. So you could say that the potential energy is greater after vaporization. All right, number 61 asks us to determine the amount of heat required to completely melt a 50-gram sample of this molecular compound at its melting point, okay? So whenever we want to find the total amount of heat that's required to do something, look at a reference table. Here we know that heat is equal to Q is equal to MC delta T, or Q is equal to MHF, which is the heat of fusion. And well, if you're trying to melt something, then you're going to use the heat of fusion, right? I'm not going to use the heat of vaporization because I'm not trying to vaporize something, all right? So whenever you're melting something, you're going to use the heat of fusion. The reason why I'm not using MC delta T is because I don't know what the specific heat capacity is, and I also don't know what the change in temperature is. All I know is that I'm melting this 50-gram object, which is its mass, and that its heat of fusion is 127 joules per gram. Right? So all I have to do here is just do 50 grams times 120 joules per gram, and I'm going to get a correct answer of 6,350 joules. So that's all I have to put here. 6,350 joules, okay? That's the only formula that gives me, or that I'm allowed to use, because that's the only information that I know here, right? So number 62 asks us to explain, in terms of intermolecular forces, why the boiling point of this molecular compound is lower than the boiling point of water at standard pressure. Or, yeah, so what governs boiling point? What governs boiling point is intermolecular forces, right? Literally what holds together the individual molecules of the substance. So for example, H2O, water, has high intermolecular forces. It has hydrogen bonding between these molecules, okay? And essentially these hydrogen bonds make it extremely hard for this water structure to be broken apart. You need to add a lot of heat to break, or a lot of energy has to be inputted in order to break these bonds between the H2Os and to turn them into gas. because again, in gas, when you're a gas or in a gas form, there's no intermolecular forces between gas particles because they're just moving at too high of an energy in order to actually form those bonds. Guess what? The only reason that they were able to get to that state is because they had to absorb so much energy to break those bonds. So you know that the boiling point of water is 100 degrees Celsius. The boiling point of this compound is only 80 degrees Celsius. So clearly, there's less of a force that's holding the molecules together, or the IMFs are weaker because it takes you less energy, less average kinetic energy to input in order to break apart those bonds, okay? So remember that the higher or the stronger your IMFs, the higher or the harder it is to boiling, right? So higher IMFs means higher boiling point. That's all that you have to do here, okay? So explain in terms of IMFs, you just have to say that water has stronger IMFs than this molecular compound. Right? Put that there and you get full credit, okay? So in this case, 53 and 55 asks us about the situation. It says that an NaOH solution and an acid-base indicator are used to determine the molarity of an HCl solution. A 15 milliliter sample of HCl is exactly neutralized by 30 milliliters of a 0.01 molar NaOH solution. Identify the positive ion in a sample of HCl. Okay, so what's happening here is that I have this beaker. It's full of hydrochloric acid, HCl. And then I'm adding, it's an HCl aqueous, so there's HCl and there's also H2O here. And then to this 15 milliliter sample, right? So if there were markings here, this would be 15 milliliters. And into here, I'm adding 30 milliliters of NaOH, okay? So before I add in the NaOH, what is the positive ion that's happening here? Well, remember that acids donate their protons, right? So this HCl is what does something called dissociation, right? It dissociates into Cl minus and H plus. Right, so the positive ion here is just going to be a hydrogen ion, H plus, right? And we could say H plus, comma, hydrogen ion. They usually like the formula plus the name, okay? That's the first point. 64 says, based on table M, state the color of the litmus when placed in a sample of original HCl solution. Well, you know here that HCl being an acid is going to dissociate, and it's going to increase the concentration of H plus ions in the solution. Why? Well, all it does is dissociate. So the majority of this HCl is going to be dissolved into Cl minus and H plus. What that means is that there's going to be a high concentration of H pluses here. Remember your pH scale. The more acidic you are, the higher the concentration of H pluses in your solution. The more basic you are, the more basic you are, the lower the H plus solution, or the concentration of H plus in the solution. So you know that water is naturally at a pH of 7. If you add the HCl, it's going to increase the concentration of H plus ions to the point where it makes the solution far more acidic and the pH is lower. Remember, the more acidic you are, the pH is 1 here, the pH is 14 here. So if we look at this litmus paper, that's going to react to the specific pH that's in the mixture, right, or in the solution. So if I look here, we're looking at litmus paper. Litmus has a pH range of 4.5 to 8.3, and it changes from red to blue. So the closer you are to 4.5, the more red you are, and the closer to 8.3, the more blue you are. Now, 4.5 lies more on the acidic side. So the paper is going to be more red because when you add an acid to a solution, you make it more acidic. So the color here is going to be red. Now finally, 65 asks us, using the titration data, determine the concentration of HCl in the solution, okay? So let's look at our reference table over here. Let's scroll all the way back down. And what we'll find here is that the titration data, the molarity of H plus, which is what we're trying to solve for, right? Molarity and concentration are the same thing. The concentration of the acid times the volume of the acid, which in this case was 15 milliliters. So Ma, which we don't know, times 15 ml has to equal to the molarity of the OH minus, which is just the concentration of the NaOH, which is 0.010 molar, 0.010 molar, times the volume of the base, which in this case is 30 milliliters. Okay, so now all I have to do is just divide both sides by 15. Divide both sides by 15 milliliters to get Ma. Okay, and if I plug that into my calculator, is 0.010 times 30 divided by 15. I'm going to get that the concentration here is going to be, if I can get my mouse over here, 0.02 molar. Okay, and that's going to be the correct answer here. So 0.02 molar, and that's the end of this video. If you have any questions, please feel free to let me know in the comments down below. Again, if you want to keep reviewing this exam, I've already included a link to the next part of this review. Hope you guys learned something, and I hope you guys have a nice day.